Good afternoon, everyone. When we talk about space, we often always ask ourselves, why do we even do space? What do we even do in space? Why do we go a few hundred kilometers, sometimes a few millions or hundreds of millions of kilometers away from our planet? Why do we actually do that? This is what I talk about today. So when we think about space, we actually shouldn't only think about going to the moon or to Mars, but we should rather think about it as creating an operating system for our planet. And space assets, namely satellites and satellite constellations, are doing exactly that. They're providing us as humans on our planet, on our precious planet, with an operating system, which can take care really of the standard everyday tasks like connectivity. It can also help us really from cleaning the trash from our Earth, trying to really take care of our planet itself. So when we take a look at some of the examples, you might think there's some small things, small decisions you take every day. For example, how did you get here this morning? Probably Google Maps, Apple Maps, one of those services told you through GPS and through the insights of other phone users what is the fastest way you actually can take to Sonkat. Sometimes it's more bigger decisions when it's around, for example, routing an airplane around a huge catastrophe or a huge wind, for example, which you don't want to definitely get into. On the other side, it's also about really connectivity. So as of today, 50% of the world's population, maybe 4.5 billion people, do not have internet access. So how do we connect 4.5 billion people to the internet, and where in many parts of the world there is no infrastructure on the ground, for example? And I can tell you it's not going to happen by burying a lot of copper cables into the ground. There has to be a better solution. And space and satellite constellations, for example, provide one of these solutions. It's also about tackling natural disasters, making sure that we actually can manage in crisis and coordinate our people on the ground to make sure that we don't lose any lives or we don't lose a lot of assets. In floods, for example, when there's floods, satellites can tell us where actually did the water come from, where is it right now, where is it going to go if it keeps raining for the next 20 minutes, for the next 2 hours, for the next 2 weeks. Where do we need to protect ourselves? And lastly, obviously, it's, I would say in general, the entire sustainability topic. There's a saying that goes, you can't manage what you can't measure. And so in order to actually take care of our planet, we also need to know what's actually happening. And so space is the ultimate vantage point to whatever we do on our planet, and this is why we go to space to improve life on Earth. To give you a few more concrete examples, space can literally provide an insight and an operating system for our infrastructure, whether it's on land, whether it's on sea. There's really the only limitation is the imagination we have and our engineers have on how we use the data. So for example, you can use satellite data to predict when is a tree gonna fall on the railroads. And before it actually happens, you can already make sure that those trees get removed such that you don't create any potential events on the rails. On the sea, it's exactly the same. How do you want to route or take the best route from A to B when your ship is going basically across the entire world and you don't have any insights into the weather, for example? How do we know about weather? Well, it's satellites telling us where and how the weather is evolving. Tracking pirates. How do you track pirates? How do you track illegal fishing? It's all being done already as of today with satellites. I think also most of you remember when a few years back an airplane just vanished from the skies. At that point in time, we only had a view, like a positioning of every aircraft every 15 minutes. Through a satellite constellation which has been launched about 3 to 4 years ago, that 15 minutes time step got reduced to 8 seconds. So as of today, we know every 8 seconds maximum or less where each and every aircraft is across the world, such that we can actually make sure there's no aircraft which just vanishes from our flight tracking radar. And what I just said before, for example, when we have floods, it's a combination of actual insights into the disaster and how we manage it. On the other side, it's also about providing the critical infrastructure, such as providing internet connectivity, connecting the people on the ground with the forces of either the military or basically the government to make sure that there's always a standing line of connection so we don't lose any human lives in this endeavor. When it's also going about space and sustainability, we obviously think about how can we even track, for example, our CO2 emissions. One of the biggest sources of CO2 emissions are actually wildfires. So roughly about 8 billion tons of CO2 get emitted every year by wildfires. And again, the solution lies in satellite and satellite data. So I want to give a small example here. Aurora Tech, which is another Munich-based company, building small satellites, and by small, I mean really small, shoebox size, 30 centimeters small, are building a satellite constellation around the globe consisting of about 100 satellites to predict when and where there's going to be wildfires. And that makes a lot of sense because we can then already tell the governments and the forces on the ground where to go to really help ourselves protect against the fires which are going to happen. Now, the way how we build and deploy satellite constellations today is vastly different from it was from 5 or 10 years ago. So today, it's really about satellite constellations, meaning there's a lot of different satellites. 10 years ago, we had a huge satellite weighing 10 tons being deployed in a geostationary orbit at 36,000 kilometers, which is a 500 million or a $5 billion project in development, super long times. And that is really changing in the commercially driven and privately financed space industry as of today to creating satellite constellations consisting of shoebox-sized small satellites where each satellite is maybe just $20, $30, maybe $100,000, where actually you can go online today, order all the satellite components through a website and get them shipped to your office or to your company. And through that mesh, you can really create a system where you can have a real or near real-time insight into every spot on Earth. And this is really equipping ourselves with the operating system of our planet that we need, whether it's for providing connectivity and high bandwidth internet, which we can deploy from anywhere between Paris to the middle of the Saharan desert, or whether it's really about tackling climate change through Earth observation. Now, what you also saw just here before, a lot of those satellite constellations, for example, are based on those satellite planes, and this is one of the drivers for us as a rocket company, obviously, because the entire deployment of those satellites change. So now you need to deploy every single orbital plane by a separate launch. And now you have, let's say, 10 satellites with 100 kilogram each, which make up for 1 ton of payload, which you need to put on a rocket. But you have the legacy rocket, which are capable of placing 20 tons into orbit. It's similar to you taking a school bus just for yourself every day from your home to the office. And it's not the most efficient way we can deploy satellites in orbit. The number of satellites and the number of satellite constellations, I think we can just take a look at the data to see how many satellites we're currently building and how big the portion is of actual small satellites. So just in the first half of 2021, we saw even more satellites deployed than in the entire year of 2020. And that is a curve which is going exponentially upwards, especially when we talk to our customers who are planning satellite constellations in 2023, 24, 25. They have vastly different requirements to placing hundreds of thousands of satellites into orbit. And so at Isar Aerospace, what we're doing is really, we're building exactly the rocket that we need for the next 10 years, and not the one which I've been using for the past 10 years. So it's a matter of size, it's a matter of quality, it's a matter of cost. How can you flexibly deploy a rocket? If you today in Europe want to buy a rocket, you have to wait 3 years until you actually can do the rocket launch, because this is roughly the time you need to actually physically build a rocket and then do the launch operations on them. What we want to try to do is we really want to punch it down to a matter of roughly about 2 weeks, such that when you want to launch your satellite, there's already a rocket ready, which has been manufactured in a fully automated rocket production, and then ready to deploy your satellites in space. Some of the technologies we use are very new to the space industry. Some of them are standard technologies from other industries which we apply in the space industry, and I want to take out a few of them here. Firstly, additive manufacturing. Our rocket engines are mostly metal 3D printed. And again, to give you a reference on the impact of that technological choice, a standard rocket engine combustion chamber takes about 1 to sometimes 1.5 years in pure production processes. Through additive manufacturing, we can bring it down to 7 days. 1.5 years versus 7 days. Obviously, all the cost, the flexibility you get through those technologies are game-changing. Secondly, we're building the first full carbon fiber-built rocket out of Europe. It's, on the one side, an extremely lightweight material. On the other side, it's also allowing us to go extra super cheap, not necessarily for the material itself, but for the way how we apply and how we manufacture the material. In that case, it's going through the process automation. So the entire structures of our rocket is fully automated in manufacturing, same as the majority of our rocket engine manufacturing. There's robots building the rocket engines and not human beings. And this really equips us with the flexibility and the scalability to really serve the commercial space industry in the endeavor of putting tens of thousands of satellites into space in the next few years. Additionally, we set out 3 years ago when we founded the company and said, what is the best rocket we can potentially build? And one of the big decisions obviously was also the type of propellant we want to use. And so we asked ourselves, why shouldn't we also just not use a more sustainable propellant? So rather than going for kerosene, which is creating a lot of black carbon and soot and deploying them in the high atmosphere layers, or what we've been doing so far in Europe, mostly also going for solid rockets, we actually changed that for a more sustainable fuel, which is a fuel actually all of you have at home in your own refrigerators. So we're using highly clean propane to propel our rockets combined with liquid oxygen, which is burning extremely cleanly, but which is also extremely high performing. So on an overall rocket level, that actually eases our overall design, which means we have simpler designs, which means we can automate the manufacturing processes behind, which means we can be flexible and low cost to deploy our customer satellites. We started off 3 years ago, and yesterday already in the opening panel, it was mentioned by Christian Angermeyer that deep tech does not necessarily have to have long timelines. It can also go fast. So 3 years ago, we were a spin-off from a university. As of today, we're having a company with more than 200 people. A sneak peek into our manufacturing on the speed we're actually putting on in the space industry. I think that's so far unheard of. We are very, very much product-driven. It's really about how can we build rockets in a super fast and flexible and low-cost way. And the only limitation are basically the freedom of designing, of manufacturing rockets, which we put on ourselves. So we're fully privately financed. Again, something which is a new approach in the European industry to say we're taking private investors' money to actually finance our rocket development and then have the governments as our customers so we can deploy their satellites at a way more flexible and lower cost solution than the standard industry solutions. We're, as of today, working across 4 different locations. We're headquartered in Munich, where all of our engineering and our administrative as well as our production efforts are. So in the past year, we've set up the full manufacturing of our entire rocket. In Sweden, we're actually testing our rocket engines. So it's already above the polar circle, very far high up north, where we have a team of about 20 people developing and testing our fully in-house developed rocket engines. We're gonna launch our rockets out of Norway. So we're also building up the first continental Europe spaceport to actually put satellites into space. And last but not least, we're very much looking forward to also coming to France to actually launch our rockets out of French Guiana. And so I hope to give you a rough overview really of what space is really about, that the space industry is actually very much commercially driven, other than just what's been mostly thought of governmentally or institutionally driven. And the space industry has a very, very bright future, especially in the next 5 to 10 years. Thank you very much.
All right. Daniel, tell me a little bit more about your rockets? Because already some people in the industry here and also in the audience are asking, are the Isar rockets reusable?
Good question. Yeah, so we're working on the reusability of our rocket. It's not going to go into the very first rocket we're building purely due to a fast time to market. We want to first get the experience, but the entire vehicle has been already designed with reusability in mind. So that is definitely something, especially on the first stage of the rocket, we're going to be able to deploy. The vehicle is already in a size class where you can do, for example, propulsive landing. We're looking into other options of reusability as well on top of that, but it's something we're very actively working on.
And maybe you can come into the diamond again, just to make sure that everybody can see you also on the live stream, because we have sort of a surrounding area here where we're supposed to stand. Do you think, and we talked about this backstage, and the question came up again, do you think space debris will be a danger for your field?
I think it's definitely something all of us need to take very seriously, because we can only solve space debris the first time right. Once there is as much space debris such that we wouldn't be able to handle it anymore, it's already too late. Similar, very, very similar to the climate of our planet, for example. I think there's a lot of technical solutions which we can try and actually make sure that we don't not only put more space debris in orbit, but that we actively take out space debris. Anything that goes towards on-orbit servicing, increasing lifetimes of satellites instead of just always putting up completely new satellites. Those are all technologies which are being worked on. I see the challenge more actually on the international cooperation, because just having one single country or even the European Union going for sustainable use of our Earth's orbit is not going to be enough. We will have to have the buy-in of the US, China, basically the entire world, every single country who's operating spacecraft to make sure we keep our orbits clean.
Because you're already mentioning all these countries, how is Europe positioning itself when we come to space compared to the US and China? Are we lacking in certain areas, or are we up to par with certain standards, especially technology-wise?
So what we're lacking definitely is private capital compared to the US, for example. Actually, the United States private capital markets put more money into space than institutional governments in Europe. So that actually is quite fascinating. We see mega rounds of billions in the US. We don't yet see them out of Europe. From a tech point of view, from a talent point of view, I definitely think we have everything that we need to do. So far, the European industry has been in a way such that we're always waiting until a politician actually wants to push something. And this is now being taken over by startups to actually say, look, we're just going to develop the technology. So I see there's a very, very bright future for the European space industry. We just need to make sure also the private capital is flowing into those startups, and that there's, for example, customer contracts from the governments who go more as an anchor customer instead of just pushing the development of specific systems.
And we have also some questions from the floor. Are you mainly considering low Earth orbit?
Yeah,
where are you going to circle?
So in general, yes, most of our customers are going anywhere between 400 kilometers and 1,200 kilometers. We're working also on the technology and stages which we can actually go towards geostationary insertion. I would say that's more a time frame of 2025 roughly. But yeah, so for now we're focusing for, I would say 95% on low Earth orbit, anything up to about 1,200 kilometers.
And going with that, because you already mentioned time frame, when are you planning your first commercial launch?
So the first commercial launch is actually going to be our third launch, because the first two have already been purchased by the German government. The first launch we're going to do is targeted towards the end of next year. It's an ambitious timeline, definitely, but as you've seen in the picture before, we're already assembling the rockets for that. And then, yeah, the first full commercial launch is going to be in probably about mid-2023.
You mentioned so many applications where satellites could be really, giving us a monitoring device. You said planetary operating device. Why are we not using this already? Because, I mean, we had wildfires, we had floods, everybody saw the news, the media. We could have used you, we could have used the satellites. Why are we not having that? What is sort of the stumbling block there?
It's a very good question, because sometimes I just don't know why we're not using it, why we're not actually buying those services from the startups. Sometimes I think literally there's the satellite is not in that drop-down menu of the government. There's copper cable, there's glass fiber, but there's no satellite connectivity. That thing just does not exist in the drop-down menu. And so I think really what we need to do is a lot of education also towards politicians, towards government officials, to saying, hey, have you actually thought about thinking outside the box for once and see, maybe we can just challenge and build a solution which is not standard, but which might be way more cost efficient. Providing internet, for example, we're not going to build glass fiber connection to every single household in the European Union. Just financially driven, it's not going to happen. But what you could do is obviously to take a satellite constellation to provide that connectivity, and then on top, use the same satellite constellation to serve the 4 billion people who, as of today, in the globe don't have internet access. So it's not only about investing in the European Union, but it's actually also, hey, you can make money out of this.
So that's actually the best way to stop the quote. Thank you so much for being here today and sharing your Isar Aerospace company with us and really the projects. Thank you so much.
Thank you very much.
We are